Hello, and welcome to today's lecture. Math Review. We're going to continue chapter 10. So, what we learned so far? We learned about sequences. Then we said we're going to build new objects using sequences. And sequence. So, review. Let f of n equals to a sub n be a sequence. So what is a sequence? A sequence is a function. It's a discontinuous function. It's a discrete function with domain equals to n. Since a sequence is a function, we can find the limit of this function. We can actually graph this function. We can find the limit of this function. And especially we're interested in limit at infinity. We're interested in understanding the end behavior of the graph of the function. So limit of a sub n while n goes to infinity, we learned that this is very similar to the limit of, almost equivalent to the limit of function f of x while x goes to infinity, the limit techniques that we learned in Calc 1. Now we're going to talk about series. So suppose you have let an be a sequence. Elements of the sequence, a sub 1, a sub 2, a sub 3, a sub n, and so on. We learned that by adding these terms, we can define a new object in math, which we call series. So the sum of the terms a sub 1, a sub 2, a sub 3, plus a sub n. If we continue, we have a new object, we call it a series, a sub k starts from 1, and it goes to infinity. So the question is, when a series is convergent, when it is divergent? So this is the question that we answered last lecture. When series a sub k starts from 1 to infinity, is convergent. When does this new object have a limit? What we did, we took partial sums to form a new sequence. S sub 1 is a sub 1. S sub 2 is a sub 1 plus a sub 2. So we take the terms of this infinite series and we form a sequence. If this sequence is convergent, then we say that our series is convergent. S sub n is a sub 1, a sub 2, a sub n. If the limit of S sub n while n goes to infinity exists, then we say that our series is convergent. Right. So we are on page 1, the rest of chapter 10. page 1. There you go. So assume this sequence. Suppose you have a sequence. The sequence is defined as n. What's the meaning of that? It means that I can list the terms of this sequence 1, 2, 3, 4, 5, and so on. Take a look at the limit of this function. This is a function. Limit of n while n goes to infinity is infinity. So the limit goes to infinity. You say that this sequence, so the sequence is divergent. Now I take this sequence, I want to form a series. Use the terms of this sequence and form a series. So the first term plus, the second term plus, the third term plus, the fourth term plus, the fifth term, and so on. This is a new object, your series. The general term is n, so you copy this down. N starts from 1 and goes to infinity. Let's take a look at partial sums of this new object, this series. Partial sums. S sub 1 is equal to the first term of this series, 1. S sub 2 is 1 plus 2, 3. So this is 1, then it is 3. S sub 3 is 1 plus 2 plus 3. So 3 plus 3 is 6. S sub 4 is 1 plus 2 plus 3 plus 4, 10. You can continue forming the rest of these partial sums. And as you can see, this sequence S sub n is an increasing sequence. And it is not bounded. So, conclusion, since Sn, this sequence, is divergent, our series, the sum n starts from 1 to infinity, is a divergent series. One interesting series is coming from a geometric sequence. Consider geometric sequence (1 over 2 to the n). First of all, the limit of this sequence, 1 over 2 to the n, while n goes to infinity, is 1 over infinity, which is 0. So as a function, the limit of the function at infinity goes to 0, so we have a convergent sequence. And if you remember the definition of a geometric sequence that we defined last time, it's defined this way: r to the n, if r is between -1 and 1, if r as the ratio is sandwiched between -1 and 1, then it is convergent to 0. If r is equal to 1, it is 1. If r is greater than 1 or r is less than -1, the limit it goes to infinity, or in general you say that it doesn't exist. This is the definition of geometric sequence. Now we take the terms of this sequence. This sequence has terms a half, a fourth, 1/8, and so on. We take the terms of this sequence and we define our new object series. Geometric series. There we go. Okay. It is a half plus a fourth plus 1/8 plus the rest of them, which is the sum of 1/2 to the n starts from 1 and goes to infinity. We formed a geometric series. So I expect you to ask, what is this sum if this geometric series is convergent? Take a look at partial sums. S sub 1 is a half. S sub 2 is a half plus a fourth, which is 3/4. S sub 3 is 3/4 plus 1/8 or 6/8, 7/8. You can continue this process and you can see if you write the first 30 terms of these partial sums, it approaches to 1. Luckily, we have a nice formula for geometric series. A geometric series, so formula for you. Formula for geometric series. If you have a times r to 0, a times r to the first power, a r squared plus the rest of them, this sum, with the condition that r is between -1 and 1, is equal to the first term, a, divided by 1 minus r. So we're going to use the formula for geometric series and find the sum of this series. So compare these together. What is your A? A is a half. What is the ratio? What is R? R can be found using the division between second term by the first term, which is a half. So the sum of these terms or this series is equal to A, which is a half, divided by 1 minus R, which is a half. You have a half divided by a half, which is equal to 1. Very well. More examples. Let me keep this formula here. We're going to use this formula. Perfect. So, question says, example, find the sum. So the terms that are given, 5 minus 10/3 plus 20/3 minus 40/27 plus the rest. Okay, perfect. So my goal is to form this sum, so I can use this formula here. The first term is 5. So here I have 5 times whatever r is raised to 0. My ratio raised to 0. Then I have -10 is 5 times 2. 5 times 2 divided by 3. Then I have 20. 20 is, okay, 5 times 4 divided by 3. What else I have? I have negative 5 times, okay, 8 divided by 3. Okay, this is 9. All right, yes, so this is 9. So I have 3 squared. And I have 27, which is 3 raised to the 3rd power, plus the rest of these terms. So I have 5, 5, 5, 5. 5 is multiplied by all of these terms. But instead of having some addition, I have negative sign here. Let me see. I have 5r raised to 0 plus 5 times negative 2 terms. Okay, if I put negative sign next to 2 terms, I can get a plus sign here. The next one is 5 times 2 thirds squared. 4 is 2 squared divided by 3 squared is 2 thirds squared. Okay, I'm good so far. Then, since it has exponent 2, even exponent, I can just write it with negative sign. Negative 2 thirds times negative 2 thirds give me positive 2 thirds. So I'm allowed to, it seems like cheating, but I'm allowed to put the negative sign here. Then I have, let's see, I have 5 times negative 2 thirds raised to the 3rd power plus the rest. So take a look at your formula. Here you have 5, negative 2 thirds raised to the 0 plus 5 times negative 2 thirds to the 1st power plus 5 negative 2 thirds to the 2nd power plus the rest of them. I have 8 times r to 0, 8 times r to the 1st power plus 8 times r to the 2nd power, and so on. I have a geometric series. 8 is 5, and my ratio r is minus 2 thirds. Since r is between negative 1 and 1, I can follow this formula. Because your r, your ratio, must be bounded between negative 1 and 1, so you can use this formula. Otherwise, it's a divergent series. So here you have the sum is equal to a, which is 5, divided by 1 minus 2 thirds. You get 5 over 1 plus 2 thirds, which is 15 over 5 or 3. Our series, the series converges to 3. Another example for you. This example says, okay, is this series 2 raised to 2n times 3 raised to 1 minus n starts from 1, goes to infinity, is the convergent series or divergent series? Okay, there we go. I see exponent n, I see exponent n. It seems like if I make some changes, I can form a geometric series. So here I have this series. 2, okay. Remember that if you have a raised to n times m, it is a m to the n or an to the m. If you have the product of two exponents, three exponents, and more, you can generalize the idea. It's actually raising the term to that new exponent. So here you have 2 raised to 2 raised to n. It's a different color, so you see what's going on here. And this guy, okay, I have negative exponent. I want to get rid of this negative exponent. I don't want that. So I'm going to flip this and write it this way. 1 divided by 3 raised to minus parentheses 1 minus. And n starts from 1, goes to infinity. So far I have 4 raised to n divided by 3 raised to n minus 1. N starts from 1 and goes to infinity. If you list some of the terms of this series, this is going to be like this. So if n is equal to 1, you get 4 over 1 plus 4 squared over 3 plus 4 to the third over 3 squared plus the rest of them. As you can see, the numerator and the denominator, they don't have the same exponent. So we cannot use this formula yet. We need to make some more changes. What I'm going to do, I'm going to multiply my numerator by 4 raised to negative 1 and 4. So now I can combine these two. I have the sum 4 raised to n minus 1 times 4 divided by 3 raised to n minus 1. N starts from 1, goes to infinity. I can take this 4, it's just a number, write it in front of the series. Now I can apply the formula. First, check to see if your ratio is between -1 and 1. So I have 4 thirds raised to n minus 1. N starts from 1 and goes to infinity. Okay, my ratio is 4 thirds. Ratio R is 4 thirds. It's not in between -1 and 1. This is greater than 1. What's the meaning of that? It means that it is a divergent sequence. Okay, perfect. So for those of you who are interested in the general geometric series formula, geometric series can be written this way. The sum A R raised to n minus 1, n starts from 1, goes to infinity, which is equal to A divided by 1 minus R, and R must be between -1 and 1. There you go. Let us go over another example. See what's going on here. Example. It says, write the number 2.317, 17, 17. So suppose that 17 is repeating here. So you have 2.317. We usually put a bar on top of the digits that we're repeating in the decimal number. So you have 2.317 bar, and it says, write it as a ratio of, write the number as a ratio of integers. Well, I have this crazy looking number. Let's see what we can do. So I have 2.3, 17, 17, 17. This guy is the sum of 2.3 plus 0.017, 0.017 plus 0.00017, 0.017 plus the rest of the decimal numbers. I'm not sure if I can do anything with the first term, 2.3, so I'm going to just copy it down here. So I have 2.3 plus, this guy is 17 divided by 1,000. This guy is 17 divided by 100,000 and the rest of them. So this is equal to 2.3 plus 17 divided by 10 to the third plus 17 divided by 10 to the fifth plus the rest of them. I can write this as 2.3 plus, I'm going to factor out 17 over 10 to the third. What's left? 1's left, 1 over 100's left, plus the rest of the terms. Okay. So I have 17 over 10 to the third, and I have a decimal number in front of the rest of these. 1 plus 1 plus 1 over 10 squared plus the rest. If you look at this expression on the right-hand side, the very first term of the series is equal to A, and your ratio is 1 over 100. Since R is between -1 and 1, you have a convergent series, geometric series. So the sum is equal to 2.3 plus 17 divided by 1,000 times A, which is 1, divided by 1 minus R, which is 1 over 100. Okay, now we have to do the algebra. See what do we have? We have 2.3 plus 17 divided by 1,000 times, here you get 1,000 divided by 9, it's 100, sorry, 100 minus 199, you can cancel out 0 and 0 here, and if you simplify, this is 1147 divided by 495. Another example for you. So by following the geometric series x to the n and 1 to infinity, then the condition that absolute value of x is less than 1, absolute value of x is less than 1, it means that x is sandwiched between -1 and 1. This is equivalent to this. This sum, if you write some terms of this series, you get x to the first power, x to the second power, x to the third power, plus the rest of them, which is equal to the first term, x, divided by 1 minus x. Again, absolute value of x must be less than 1. So I expect you to ask, what happened to the rest of it? Take a look at this. If you factor out x, you get 1 plus x squared plus the rest of the terms. So this guy is actually the format of your geometric series. If you forget about a, so if you list some of the terms here, you have a, 1 plus r squared plus the rest. So this is going to be x divided by 1 minus x. A is just x. Note that if you have a series like exactly the same general term, x to the n, but x starts, so let's see, n starts from 0 to infinity. Then if you plug in 0, it's going to be x to 0, plus x to the first, plus x to the second, plus the rest of them. This is just 1 plus x squared, plus the rest of them. Your a, your very first term, is not x. It's going to be 1. So the sum is equal to 1 divided by 1 minus x. And note that absolute value of x must be less than 1. So note the difference between these two series. One of them, the index starts from 1. The other one, the author says, okay, the index starts from 0. Another interesting series is sometimes they call it telescopic series. The sum 1 over n times n plus 1, n starts from 1 and goes to infinity. Okay, they have a general term. It has nothing to do with the geometric series. So 1 over n times n plus 1 is equal to. Let us use the composition of fractions and write it as a over n plus b over n plus 1. Our goal is to find a and b. So if you take common denominator between these two, it's going to be a times n plus 1 plus bn divided by n times n plus 1. Left-hand side and right-hand side must be equal to each other. So the denominators are the same, numerators must be the same as well. So it means that 1 is equal to an plus a plus bn. On the left-hand side, you only have a constant. What's the meaning of that? It means that your n is multiplied by 0. The coefficient of variable n is 0. So if you take these two and factor out n, the coefficients a plus b must be 0. 0n plus 1. A plus b as the coefficient of n is equal to 0. So a plus b is 0. And a as a constant is equal to 1. So if you solve this equation, b is equal to minus 1. So 1 over n plus 1 can be written as, this sum can be written as 1 over n minus 1 over n plus 1. N starts from 1 and goes to infinity. So let us write some terms of the partial sums Sn. So my Sn is equal to the sum, k starts from 1 to n, 1 over k minus 1 over k plus 1. If Sn is convergent, then for sure you can say that your infinite series is convergent as well. So here you have, if you plug in 1, you get 1 over 1 minus 1 over 1 plus 1 plus 1 over 1 plus 1 minus 1 over 1 plus 2 plus 1 over 1 plus 2 minus 1 over 1 plus 3 and so on. And the last term, the last two terms, negative 1 over k plus 1 over k minus 1 over k plus 1. Very good. This is 1 minus a half plus a half minus a third plus a third minus a fourth plus a fourth plus minus a fifth. So the rest of the terms minus 1 over k plus 1 over k minus 1 over k plus 1. As you can see, you end up with opposite terms. So positive, negative, positive, negative. You can cancel out all middle terms. What's left? The first term is left, and the last term. Sn is nothing but 1 minus 1 over the last term here. We have n, sorry, this is n, not k. Let's fix that. One over n plus 1. So if we take the limit of Sn while n goes to infinity, this is 1 minus 1 over infinity, which is 0. So it is. So this series converges to 1. This is your conclusion. So our series converges to let's move on to the next important series. We call this series harmonic series. First of all, remember the sequence. This is an important example, guys. Suppose you have your sequence 1 over n, 1 over n. Okay, if you list some terms of this sequence, it's 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. If you take the limit of 1 over n while n goes to infinity, it is 1 over infinity or 0. So what do you have here? You have a convergent sequence. It converges to 0. So we're interested in forming a series. We're going to use this sequence and form a harmonic series. Harmonic series. What is interesting about this series is that this series is a divergent series. So you have series 1 over n, n starts from 1 and goes to infinity. This is 1 plus a half plus a third plus the rest of the terms. If we form the partial sums, then S of n, the sequence of partial sums, is an increasing, unbounded sequence. So Sn goes to infinity and the harmonic series series is divergent. So remember this example. This example is very important. We're going to go over one theorem and you're going to derive some conclusions based on that theorem. One important theorem. So this theorem says, if you have a series, if series an and starts from 1 to infinity is a convergent series, is convergent, then we can conclude that the limit of the general term while n goes to infinity is 0. So the contrapositive of this theorem says if the limit of a sub n while n goes to infinity is not 0, for sure you can say that a series sigma a sub n starts from 1 to infinity is a divergent series. Very important theorem. Let's go over one example to apply this theorem. Show that the series n squared over 5n squared plus 4 and starts from 1 to infinity is divergent. Well, I'm going to use the theorem. The theorem, above theorem, says if the limit of my general term is not 0, for sure I get a divergent series. So a limit of n squared over 5n squared plus 4 while n goes to infinity. This guy is equal to 1 over 5, which is not 0. The limit of the general term is never 0. So, since the limit of the general term is not 0, so the series is divergent. Okay, perfect. Next example. We are on page 7. Example says, find the sum . So here you have this series 3 over n times n plus 1 plus 1 over 2 to the n, and starts from 1 and goes to infinity. There. So let's try to analyze this series and see what do we have. The very first one is actually the breakdown of telescopic series that we saw before, and the second one is nothing but the geometric series. So you can rewrite the first term as 3 times 1 over n minus 1 over n plus 1. And the second one can be written as a half raised to n. And starts from goes to infinity. So this one is 3 times 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 and the rest of them, plus you have a half plus a fourth plus 1 over 8 plus the rest. So as you saw before, you can get rid of middle terms and the n value is equal to 3 times 1 minus 1 over n plus 1. And here you have just a geometric series, which is the first term is a half a divided by 1 minus the ratio, which is a half. So this is 1. When n goes to infinity, you have 3 plus 1, which is 4. So this series converges to okay. Let's just give a quick introduction to improper integrals. Introduction to improper integrals. So when we're talking about improper integrals, it means that one of the boundaries of the integral is not a constant. It's like infinity. So you have, for example, the integral of f of x. For example, your x ranges between a, and instead of stopping at b, it goes to infinity. To find this integral, we take the limit of this integral, a raised to the upper bound is k, while k goes to infinity. Exactly the same as your regular integral, but instead of stopping at k, after finding your integral, you have to take the limit while your upper bound or your lower bound, sometimes it's the upper bound goes to infinity, sometimes the lower bound that goes to infinity. Take the limit of it and evaluate your outcome while k goes to infinity. So this is an introduction to improper integrals. Why we need that? We need that here for series. So let me write a quick note for you. When it comes to series, you either have nice series. What do I mean by that? You have, for example, series of harmonic series and 1 to infinity. You know that it's a divergent series. Or you have geometric series, 1 over, let's write r to the n and starts from 1 to infinity. So for this guy, if r is between -1 and 1, this is a divided by 1 minus r, so geometric series. Or you're dealing with telescopic series, nice series, 1 over n plus 1, and starts from 1, goes to infinity, which is convergent to 1. So again, when it comes to series, you either have nice series or you have series that are not nice. You have to apply other techniques, not nice series. in this case, we have to apply some theorems, some techniques to analyze those series. So if you have a series like this, then you're lucky. It's easy to analyze that series. Later on, we're going to talk about P-series as well. But we need, for example, improper integrals to analyze not nice series. Let me write a theorem for you. Theorem. So let f of x be a continuous positive and decreasing function. On the given interval 1 to infinity. Then you have the following conclusions. If the improper integral f of x 1 to infinity dx is convergent, then this series f of n from 1 to infinity is also convergent. And if your integral 1 to infinity, improper integral of f of x dx is divergent, then its equivalent series and 1 to infinity is divergent. Important theorem to deal with not nice series. Okay. Example. Let us see one example and apply this theorem here. So analyze this series. You have this series 1 over n squared plus 1. N starts from 1, goes to infinity. Very well. Here I have this series. It's not a geometric series. It's not a telescopic series. What is it? How to analyze this? Well, we learned about this nice theorem. Let us apply this theorem. First of all, 1 over n squared plus 1 is positive. Is positive. 1 over n squared plus 1 is continuous. 1 over n plus 1, n squared plus 1 is also decreasing. N squared plus 1 is decreasing. So it satisfies all of these conditions. Continuous, positive, and decreasing. So we can apply the theorem, the integral of the function 1 over x squared plus 1 dx 1 to infinity is equal to the limit of the integral 1 to k 1 over x squared plus 1 dx. We know that this is inverse tangent function. This is the limit of inverse tangent of x. X goes from 1 to k, and k goes to infinity. Okay, this is equal to inverse tangent k, while k goes to infinity, minus inverse tangent of 1. We know that inverse tangent goes to infinity at pi over 2. Inverse tangent goes to infinity at pi over 2. And inverse tangent of 1 is pi over 4. If you take common denominator between these two, you get 2 pi minus pi, which is pi over 4. So what's the conclusion? Since the integral, since the improper integral is convergent, so as our series. So let us define P series. So P series is defined as the sum of 1 over, let's say, instead of x use n to the p, m starts from 1 to infinity. If p is a number greater than 1, guys, p as the exponent. If p as the exponent is greater than 1, then we have a convergent series. And if p is less than equals to 1, if your exponent is less than equals to 1, then you have a divergent series. We can check this using integral theorem or integral test. For example, take a look at this series. 1 over n to the third, n starts from 1 to infinity. Is this a convergent series? Is this a divergent series? First of all, 1 over n cubed is positive. Second of all, 1 over n cubed is continuous. We don't have any problem with this. 1 over n cubed is decreasing. So the theorem tells us if the integral 1 to infinity of 1 over x cubed dx is convergent, then our series is convergent. So this guy is equal to the limit of integral 1 to k goes to infinity of 1 over x cubed dx. This is equal to the limit of integral, so this integral is just x to negative 3 dx, 1 to k goes to infinity. This is equal to limit of x raised to negative 2 divided by negative 2, while k goes to infinity, 1 to k. So this is equal to the limit of 1 over minus 2x squared, while k goes to infinity, 1 to k. So here you have the limit of 1 over minus 2k squared, k goes to infinity, minus, if you plug in 1 over negative 2 times 1. So limit 1 over infinity is 0, plus a half, and as you can see, you have a convergent integral, so the series is convergent. So as I mentioned before, you can use your integral test to check P series. But in general, when you have a P series, if you have 1 over n raised to different exponents, if that exponent is greater than 1, We can say that, hey, I have a convergent series. If it's less than or equals to 1, it is divergent. Okay, next example. Page 9. So the question says, analyze this series. Series ln of n divided by n starts from 1 and goes to infinity. Okay, this is a crazy looking function. This is a crazy looking series. It's not a p-series, it's not a geometric series, it's not a telescopic series. So we have to check to see if it satisfies the conditions for that theorem. First of all, ln n divided by n is positive. You can graph it using Desmos. 2 ln n divided by n is continuous. And this is a decreasing function. You can take the derivative, and the derivative is negative. ln of n divided by n is decreasing. Its derivative is negative. So let us apply the theorem. All conditions are met. The integral, improper integral, 1 to infinity of ln of x divided by x dx. This is equal to the limit of integral 1 to k. K goes to infinity, ln of x divided by x dx. We can use u sub method. This is equal to the limit of integral u, which is ln of x, du, and k goes to infinity. So this is equal to limit of a half u squared. Your u is ln of x, ln of x squared. X ranges between 1 to k, and k goes to infinity. Okay, perfect. I have limit of a half ln of k squared, k goes to infinity, minus, if I plug in 1 for ln, it's going to be 0. ln of k at infinity is infinity. So, since the integral goes to infinity, it is divergent, so as your series. Since the integral goes to infinity, so our series is divergent. Okay, perfect. So we have another technique. We can compare two series this way. So let sigma am and sigma bm be two series. Suppose am is less than the second series bm. We have two cases. If the smaller series is divergent, if this series goes to infinity, then so as bm. if the bigger series, sigma Bn is convergent, then so as the smaller series An. That's how we can compare two series. First of all, you need to make sure the first series is less than or equal to the second series. Then, if the smaller series is a divergent series, then for sure the larger series is divergent. But if the larger series is a convergent series, the smaller series is also convergent. For example, let's look at one example to feel more comfortable about this technique. You have series 5 over 2n squared plus 4n plus 3. There you go. When you have series like this, you have something on the denominator. Take a look at the term with the largest exponent. You can compare these two series together. So this is your first series, 5 over 2n squared plus 4n plus 3, and series 5 over the largest term, 2n squared. n starts from 1, goes to infinity, n starts 1, goes to infinity. If you increase your denominator, the fraction gets smaller and smaller. So this series is less than equals to this series. Think about it this way. Suppose you have 1 over 2 plus 4 plus 3. This is a fraction. This is 1 over 9. If you forget about these two numbers, you get a half. Of course, 1 over 9 is less than a half. So you can think about these two series this way. Getting back to pre-algebra and just thinking about numbers. If I add more numbers to my denominator, my whole fraction is getting smaller and smaller. Okay, this is a p-series. I already know the behavior of this p-series. This is 5 over 2 times 1 over n to 2. P is 2, the exponent is 2, exponent is greater than 1. And I know that this series is a convergent series. Convergent series. Okay, since your Bn, series Bn, the larger series is convergent, so as your original series, it is convergent as well. Okay, another test for you. So we are on page 10. Again, suppose you have two series. Let sigma An, sigma Bn be two series. Sometimes this test actually is a good test, an easy way to analyze two series. Take the limit of An divided by Bn or Bn divided by An. It's not very important. While n goes to infinity. If you take the limit, and if this limit is equal to a constant like c, and if c as a constant is positive. If you have a constant which is positive, then both sigma an, sigma bn are convergent, or both sigma an, sigma bn are divergent. Note that if C is equal to 0, if C is negative, we have to use a different technique. This technique doesn't work. It works only for C greater than 0. Okay, let us take a look at one example. You have series 1 over 2 to the n minus 1, n starts from 1, goes to infinity. Whereas I have one series. I need to come up with a series which is similar to this series and helps me to find the limit. Since this series is similar to geometric series 1 over 2 to the n, I'm going to use this limit and comparing these two series. You can find the limit of, suppose this is your an, suppose this is your bn, it doesn't matter. 1 over 2 to the n minus 1 divided by 1 over 2 to the n. So if you rewrite this limit, you get a limit of 2 to the n divided by 2 to the n minus 1, while n goes to infinity. 2 to n goes to infinity much faster than this constant negative one. So you can ignore the negative one. 2 to the n divided by 2 to the n is equal to 1. So your C is equal to 1. Is it positive? Yes. Now I can decide about this series. Your conclusion is, since C is positive and geometric series 1 over 2 to the n, the ratio is a half between negative 1 and 1, is convergent, so as series 1 over 2 to the n minus 4. Alternating series. Series of this form, sum negative 1 to the n times a term like bn, n starts from 1, goes to infinity. This series is called alternating series. If bn is decreasing, it means that if you take the derivative of bn, and bn has derivative and negative derivative. So if bn is decreasing, and if the limit of bn while n goes to infinity is equal to 0, if these two conditions are met, then the alternating series is convergent. let's put a negative sign here, negative 1. One example for you. Consider this series. Series -1 n to -1 times 1 over n and starts from 1 to infinity. Okay, this is your Bn, the general term. First of all, Bn 1 over n is decreasing. Of course, if you take the derivative of 1 over n, this is equal to -1 over n squared, which is always negative. The derivative is negative, so Bn 1 over n is decreasing. Then the limit of 1 over n, while n goes to infinity, is equal to 0. And we say that, hey, since these two conditions are met, my alternating series is convergent. So since these two conditions are met, so our alternating series is convergent. Very well. We say that a series is absolutely convergent if its absolute value is a convergent series. So absolutely convergent. If series absolute value of an and from 1 to infinity is convergent, then we say that our series is absolutely convergent. So absolutely, absolute value. Example, consider this series. Series -1 raised to n minus 1 over n squared and starts from 1, goes to infinity. Question says, is this series an absolutely convergent series? Very well. Let us take the absolute value of this series and make sure it is convergent or it is divergent. So the absolute value of -1 raised to n minus 1 divided by n squared and starts from 1 to infinity is equal to absolute value of -1 raised to any exponent is positive 1. So you get the sum 1 divided by n squared and starts from 1 to infinity. And of course, this guy is a p-series. This is a p-series. P is equal to 2, greater than 1. So this series is convergent. So our series is absolutely convergent. Okay, let's see what's left. ratio test, and root test. So two important tests, ratio tests and root tests. And root tests. Very well. So if the limit of absolute value of an over an plus 1 over an, while n goes to infinity, is equal to a number like L, and L is less than 1, L is less than 1, then your series is absolutely convergent. Then sigma an is absolutely convergent. If L is greater than 1, then it is divergent. Then the series is convergent. Note that L greater than 1, it can be infinity as well. So this is your ratio test. For the root test, we take the nth root of our general term. If the nth root of absolute value of an is equal to L, and if L is less than 1, then the series is absolutely convergent. So the conclusion is the same. Then sigma an is absolutely convergent. And if L is greater than 1, then your series is divergent. Root test and ratio test. Okay, let's go over two examples to see what's going on here. Suppose you have this series. Series -1 to the n to the third, divided by 3 to the n, and starts from 1 and goes to infinity. So let's apply ratio test for this series. We're taking the limit of absolute value of an plus 1. It means that you have -1 raised to n plus 1, n plus 1 to the third, divided by 3 raised to n plus 1. The whole thing is divided by an. -1 to the n plus 1, n to the third, divided by 3 to the n. We're going to take this limit while n goes to infinity. Note that since you have absolute value, you can get rid of -1. This is equal to the limit of absolute value of n plus 1 to the third times 3n divided by n cubed times 3 to the n plus 1. N goes to infinity. This is equal to the limit of absolute value of n plus 1 to the third, 3 to the n, divided by n cubed times 3 to the n times n goes to infinity. So of course I can cancel out 3 to the n and 3 to the n. Note that the limit of n plus 1 to the third divided by n to the third while n goes to infinity is equal to 1. They have the exact same exponent, the same degree. So if you take the limit, they go to infinity at the same speed. So you can cancel out these two. You can actually say that, hey, I have plus 1 as the lower term. I can ignore this. I get n cubed divided by n cubed, which is 1. So this is equal to 1 over 3. You have a third, which is less than 1, less than 1. So we have the convergence. One last example for you. See how we can apply root test. Example, you have series 2n plus 3 divided by 3n plus 2 raised to n, and starts from 1, goes to infinity. Okay, I'm going to apply my root test here. I take the limit, I take the nth root of my an, and then I take the limit while n goes to infinity. I have 2n plus 3 raised to, sorry, write the denominator here without separating these, it's easier, divided by 3n plus 2 raised to n. Since the exponent and my index are the same, I can cancel out these two and get rid of the radical. So here I have the limit of 2n plus 3 divided by 3n plus 2 while n goes to infinity. Okay, here you can get rid of 3 over 2 because these two are lower terms. And you have 2n divided by 3n, you can cancel out n and n. So this limit, this L is equal to 2 thirds, which is less than 1. L is less than 1. So you get an absolutely convergent series. Absolutely convergent series. Let me add the limit here. Don't forget we are taking the limit.